So there's really two main topics for this exam. Can you graph a conic section? So can you graph a parabola, ellipse, or hyperbola? And remember, that could be one of two ways. Number 1 and 2, those are in standard form. And then number 3 here is in general form. So you need to be able to graph when it's in either form, standard form or general form. And then number 4 is a rotated conic. So you don't have to graph those by hand, but you do need to be able to identify the rotated conic using, there's some theorems on the back cover there. So that's the first topic. Can you graph a conic and identify the conic? The second topic is working with polar coordinates. So can you switch back and forth between rectangular and polar coordinates? Can you plot a couple of points that are given to you in polar form? And can you convert an equation back and forth between rectangular and polar coordinates? So, number 1, it doesn't tell you which type of conic it is, but if you look at it, you see that only one variable is being squared. So you would guess that it's a what?
Parabola.
Parabola facing which way? It's one of the horizontal ones, yeah, because the y variable here is the one. Yeah, the y variable is the one being squared. What we need to do, though, is that right side needs to be also in factored form, because we've got to be able to figure out what the horizontal shift was. We know that there's a vertical shift up 2 units, but we don't know what the horizontal shift is. So first thing we do is rewrite the equation. Because now that tells us there's a shift to the left 3 units. And then, like I said, there's a shift up 2 units. So left 3, up 2, that's going to be where the vertex is. So I'm going to go ahead and just make that my origin, where that vertex is. And the other reason for factoring that right side is that this 3 is that coefficient that you make equal to 4p. So remind me, what is this going to help you find? Focus. Yep, this is going to help you find the focus. So if we solve for p, divide by 4. P equals 3/4. So we know it's 3/4 of a unit away from the vertex, which is right here. So now we've got to think, okay, we already decided that it was a horizontal parabola, and the fact that P is positive tells us that the focus is to the right of the vertex. So eventually we're going to be graphing a parabola that opens to the right because P had a positive value. But here's our focus. It's 3/4 of a unit to the right of the vertex. Now let me go back and ask another question. P doesn't also tell you the focus. It also tells you one other important thing, the directrix. It's directly opposite. So the directrix is 3/4 of a unit on the other side. And the directrix isn't a point. Remember, the directrix is a line. So there's your directrix. If it's going to be too messy to label everything on the graph itself, you can just write out somewhere on the problem. All right, with the vertex, we already had that point on there. It was -3, 2. How would I describe the location of the focus? I know it's up 2 units. Yeah, so the vertex was 3 units to the left, so the vertex was at -3, and then I shifted to the right 3/4 of a unit, or 0.75, so it would be -2.25.
Did you know to go to the right because 3/4 was positive?
Because 3/4 is positive. That's a good question, and we're talking about what if P had been negative? Go to the left. What if it wasn't y that was being squared? What if it was x that was being squared? Then P would go up or down. P's positive goes up, its negatives goes down. We're clear on that?
So I'm confused still on the focus, how you got the...
Which, where?
Well, so the 2 makes sense. We're obviously solving for...
Which part of the focus? The actual value, 3/4, or where it is on the graph?
So do we add the
Now since it moved to the right, it doesn't affect the y value, it affects the x value.
For the x value.
So you add 0.75 to negative 3 and you get negative 2.25.
Oh.
Does that answer your question?
Yeah.
Okay. And then the directrix, because it isn't a point, you actually have to name it with an equation. And since it's vertical, we talked about this, vertical equations always have, or vertical lines have an equation of x equals. And it's 3/4 of a unit to the left of where the vertex is, and the vertex was at x equals negative 3. If we go 3/4 of a unit to the left, negative 3.75. So the directrix is x equals negative 3.75. Now I know we've had some good discussions on where to proceed from here. We only have one point on the graph so far, it's just the vertex. You got to have 3 points. And especially when the parabola is sideways, we seem to have had some questions on how do we get the other point. So I'm just going to go ahead and make a quick xy table. Really, that's the most organized way to keep track of finding x or y values, in my opinion. But we already know one point. It was the vertex, negative 3, 2. I know typically when we're choosing values to plot, we would choose x values, and you can still do that. I'd recommend, though, that we don't choose x values, that we choose y values. In this particular case, because if we choose x values, we're going to end up having to take a square root or solve a quadratic equation, which we may not want to do. So I'm going to choose some y values close to this y value here. So y equals 1, maybe. If I choose to let y equal 1, and you plug it into the equation, y becomes 1, so 1 minus 2 is negative 1, negative 1 squared is 1. So then we have this equation, 1 equals 3x plus 9. So if you subtract, you get negative 8 equals 3x. So x equals 8, negative 8 thirds. 8 thirds, so that would be negative 2.6. So there's another point on the graph, negative 2.66, comma 1. And then we can use symmetry to reflect that point on the other side. So that would be negative 2.66, comma 3. Okay, let's talk about what could be different about this problem. We already talked about what if x was the variable being squared and not y. What changes here? It's opening up or down. If p is negative, on this problem, if y is squared and p was negative, that means it would open up to the left, and the directrix would be on the right side. That's really all that could be changed on a problem like this. What questions do we have? Okay. Question 2, hyperbola. And we know that how? Minus there, yep. If that were a plus, it'd be an ellipse. So, you got to remember with a hyperbola, it doesn't matter which one of these is bigger than the other to determine which one is A or B. What matters is which one is associated with the positive fraction. So x plus 4 squared is the positive one. So that automatically makes this A. So if a squared equals 16, then a equals 4. And then over here we have b equals 3. And those two values are going to help us get the width and the length of the central box for the hyperbola. But we do need to know where the center of that central box is going to be, and that's where we use our transformation. So we're going to the left 4 and down 2, according to those transformations. Left 4, down 2. And once you have that center, you use these values, a equals 4, b equals 3. Since a was associated with the x variable, that's going to be horizontal. So from your new center, you're going to go 4 units to the left and 4 units to the right. And
If y was in the beginning, it would have been.
yeah, so if this were a y right here instead of an x, this would still be a, but then you would go up and down 4 units instead of left and right. And then b is up 3 and down 3 since it's associated with the y variable. So up 3 and down 3. So like I said, those values just give you the width and the height of your central box. So once you have them, just go ahead and carefully as you can draw that central box. What the heck is that central box even there for? Yeah, your 2 crisscrossing slanted lines there that help you get the shape. So we got the asymptotes, we got the central box. And you got to remember now what kind of hyperbola this is. There's 2 kinds. There's the ones that are facing out left and right and the ones that's facing up and down. And since the x variable was the one that's listed first with the positive variable, it tells us that this is the horizontal one. So that makes this point right here one of your vertices, and this point right here the other vertex. Okay, so make sure when you draw the hyperbola, it goes through that point here on the left, and it goes through that point on the right. So those 2 curves right there, that's the hyperbola. We're just missing the 2 foci. Yeah, we're missing the 2 foci. So the formula is a squared plus b squared for a hyperbola. So that's going to be 16 plus 9. So the foci are located 5 units away from the center of that central box. So that places one of them here. And one of them there. Again, it's kind of small to write in the graph what the location of all those points are. So if you wanted to label them like point A, point B, and then off to the side, give the coordinates of those points, you can do it that way. I label the foci always with a F1 and F2. So let's at least give the location of the 2 foci. So the one there on the left, the focus on the left, this one here, the location, we know it's down how many? We know it's down 2 units, so it's -2. And how far to the left is that? It was 5 units away from this point right here, but that point was already 4 units over, so that's -9, yeah. So -9, -2 for the first focus. Second one, looks like it's 1 unit to the right, 2 units down. So let's talk about what could be different. If I had switched the variables, that one was a y and that one was an x, what changes? Yeah, it's the one where it's up and down. It will also change, the left and right, moving left and right, but that's really all that could potentially be different on a problem like this. What questions do we have about hyperbolas? Or is it hyperbole? No, it's got to be hyperbolas.
I think it could be either or.
Because isn't hyperbole a grammatical term?
Well, yeah, but that's what
This
we
is
need
the epitome of hyperbole.
The epitome? I don't know. Hyperbolas. Did we finish this one? I think we did. Okay. All right. Question 3. This is one where you got to complete the square because it's in general form. We know at least it's not a parabola because, well, we're assuming it's not. Let's put it in general form really or standard form to find out for sure. I'm going to group the x terms together and factor out the 9, then group the y terms together and factor out the 4, and then move this 4 to the other side, make a -4. We get with that so far? I just factored out a 9 from the x terms. I factored out a 4 from the y terms so that I can complete the square. So the value that completes the square for the x expression, you got to remember to take half of this middle term, which is 2, and then square it. So I'm going to put a plus 4 inside the parenthesis, but I've got to balance out the equation by adding a 36. Why a 36? The 9 times 4. Yep, and that's one of the common mistakes is instead of just focusing on that and saying, well, I added 4. No, you really didn't add 4. You added 9 plus 4. So, and then here, the value that completes the square is half of -2, which is -1. Then you square that, so it's a plus 1. But if you account for the 4 that was factored out, it's really a plus 4. So now the right side is still a 36 because we just added and subtracted 4. But then the x variables factor into x plus 2 times x plus 2 or x plus 2 squared. And then the y variable expression is y minus 1 times y minus 1 or y minus 1 squared. Still not standard form because we don't have, it's supposed to equal 1 if this is going to be a hyperbola or a parabola, or sorry, an ellipse. So we need to divide by 36, divide by 36, and divide by 36. Now, I want to bring up something here that doesn't necessarily have to do with this problem. You may have seen it in the homework, and it is, I suppose, a possibility. It's really convenient that we have fractions there that simplify so nicely, right? 9 over 36 and 4 over 36. It doesn't always happen that way. Let's say that it was a 40 over here and not a 36. Now we're dividing by 40. Well, that one simplifies, I guess. But this one doesn't. 9 over 40 doesn't simplify, so what do we do with it? We can reduce it as far as we can. But to be technically standard form, we have to have x plus 2 squared over something here. We can't have a coefficient in front of that parenthesis. So the way you would handle this, if you were ever in a situation where that fraction doesn't simplify, is you just invert the fraction and write it here like this. And that's your denominator, 40 over 9. Okay? Because let's talk about this. What is the 9 over 40 doing to this parenthesis right here? It's multiplying. If you divide by the reciprocal, it's the same as multiplying. So that we didn't really change the operation. We're just dividing by the reciprocal, which is the same as multiplying. We clear on that? I know it doesn't happen often, and like I said, on this problem, we were lucky that everything simplifies nicely, but it doesn't always happen that way. So divided by 36, 9 over 36 gives us a 4 down at the bottom. And then 4 over 36 is going to give us a 9. So now we know it is an ellipse. And we're moving to the left 2 and up 1. Those are our transformations. Of the two values in the denominator, 4 or 9, which one is a squared? For ellipses, it's always the largest one. For ellipses, it's the largest value is a squared. So let's review this. For ellipses, how do you determine a squared? Whatever the largest one is. Okay. For hyperbolas, how do you determine which one is a squared? Whichever one's associated with a positive fraction. It doesn't have to be bigger or smaller, it's just whatever one's with a positive. So for this problem, number 3, because it's an ellipse, a squared has to be 9, which means a equals 3. And then b squared is 4, which means b equals 2. Okay? So that makes this a vertical ellipse. It's going to be longer in the vertical axis than it is in the horizontal. Okay? So starting from that center point, you're going to go up 3 and down 3. And I went up 3 and down 3 because my value for A was associated with the y variable, which is vertical. Okay. And then since B here is associated with the x variable, then I'm going to go to the right 2 and to the left 2. So that gives me the endpoints of my major and minor axes there. And I've never been good at drawing these things. But that's not bad right there. I gotta say. I'm pretty proud of that one. So that point there is the point 0, 1. The other endpoint is 1, 2, 3. That's -4, 1. The endpoint of the major axis there is -2, 4. And what do we have there? -2, -2. So we've labeled the endpoints of the major and minor axes. The only thing we're missing are the 2 foci. What's the formula for ellipse? A squared minus, yeah. So c squared is 9 minus 4, which is 5. So the values for c are plus or minus root 5, which is what, 2 point something, 2.2 maybe? 2 point what? 2.24, okay. Which direction? Up, down, left, right? Up and down, because this is the major axis is the vertical direction, and the foci always go on the major axis. So I'm going to go 2.24 up from the center. And 2.24 down. And it's a little tight inside that ellipse to label those points. So I'm just going to call one of them focus 1 and focus 2. And give their locations out here. So I was already up 1, and then I went another 2.24, so that's 3.24. And then, well, I got to think for a second here. That second focus, we're -2. We're supposed to go down 2.24, but then we back up 1. So yeah, -1. -1.24. That's really the extent of graphing your conics. You got to be able to graph the parabola, hyperbola, ellipse. There's going to be 3 questions just like this. One of them you're going to have to do completing the square, and it may not be of a parabola or what was this there, an ellipse. It could be completing the square on a hyperbola or parabola. So don't just study problems where you complete the square to form an ellipse. Look at some also where you may have to complete the square for a hyperbola or a parabola. You catch my drift there?
Yeah.
Okay. Because these problems are similar to the ones on the exam, but these aren't the exact same. They're the same type of problem, but not the exact same problems. So make sure you don't just focus on, yeah, I can solve number 3, I'm good to go. You got to decide, can I solve problems like number 3 or problems like number 2? And think about what could change, and if you're still comfortable, if things change, being able to solve that problem. Okay. So this one here, let's see, question 4. This was from 6.4. Didn't spend a lot of time in 6.4, honestly. And there's, like I said here, there's 2 basic things you need to do, and the formulas were provided for you. So number 4 isn't intended to be a super tricky problem. You need to determine the rotation and what type of conic it is. And those 2 formulas are on the back side of that front page there. So the conic identification theorem is just part of the quadratic formula. You do have to remember which one is A, B, and C. So A is 6, B is -6, and C is 14. So B squared becomes negative 6 squared. And really, the actual number here isn't what's important. All that matters is a positive, negative, or does it equal 0? And just looking at this, looks like it's going to be negative. And that's all you need to know. Is it negative, is it positive, or is it 0? I know it's not 0 because 4 times 6 times 14 isn't 36. So I'm going to say that this is less than 0. What does that tell me? Yeah. It means this is an ellipse. So right off the bat, I know it is not either of those. The other thing now is using the rotation theorem is what it's called. The cotangent of 2 alpha, where alpha is your rotation. So here we have cotangent of 2 alpha, 6 minus 14 over negative 6. Cotangent 2 alpha is 4/3. Now what? The way we did this, if you remember, if you were here in class, is most calculators don't have an inverse cotangent button, but most calculators have an inverse tangent button. And cotangent is just the reciprocal. Remember, cotangent and tangent are reciprocal. So we can change this whole equation into tangent of 2 alpha if you switch the fraction to its reciprocal equals 3/4. So then
Why don't we just have the original equation be tangent to alpha b over a minus c then?
I suppose you could. Just the way that the formula is derived, if we want to, I didn't show you the derivation, but just how this formula came to be. It's derived using cotangent, so they just stick with cotangent. But
Wouldn't the inverse of tangent still be cotangent, so then they just like switch back to
it's 1 over, so yeah. Is that what you're asking?
yeah.
It'd be 1 over, but
I mean, like,
it's all the same.
I mean, aren't you gonna do
Where were we? What are we doing here?
Inverse tangent.
Oh, so calculator time. Inverse tangent of 3/4 is something on a calculator. Are you, what mode are you in? Do you
Well,
see?
you know what? I didn't do it the right way. I didn't flip that fraction.
Oh. It is 36. It's supposed to be 36, but make sure you're in degree mode for this problem. This one's got to be in degree mode. If you're in radians mode, it'll 36.87. So that's 2 alpha. If we divide that by 2, now we get alpha equals 18.4 or something. So what this means is your ellipse was rotated counterclockwise 18 degrees, roughly 18 degrees. So we're deciding between these top 2 graphs. And I guess I should have put A, B, C, or D now that I'm thinking about this. I'm going to say this one is A and this one is B. Which ellipse has been rotated counterclockwise? Because it's positive and it's A, so you're needing to identify this one. Now, if alpha turns out to have been negative, remember negative angles rotate clockwise, so then this one would have been rotated 18 degrees negative, right? There was, if I remember right, a problem on the homework or on the review. I can't remember where we ran across this one. This can happen, and it makes it tricky when it does, so I just want to make sure we talk about it now. It doesn't affect this problem, but how should I start this one? Okay. If you're using this formula, and let's suppose that A, B, and C were all, let's say it's all 6. A, B, and C are all 6. what happens? Let's say you're doing a different problem and A, B, and C are all the same number, like 6. You get 0. Okay, so then you get cotangent of 2 alpha equals 0. So what's the problem now with what? So think about how we proceeded just barely. Once we got to this step, how did we proceed?
Flipped it.
We flipped it. But the problem here is 0 is the same as 0 over 1. So if I flip that, it's domain error. We're dividing by 0, which we can't do. So what are we doing here?
But it was not rotated.
It is still rotated, but we can't proceed by switching this to its reciprocal and doing inverse tangent.
Could you do inverse one over inverse tangent and keep it right at
Yeah?
would that work?
Yeah. What I was going to suggest, though, is that will work, but do you remember the definition of cotangent? Okay, right.
It's cosine over sine.
Cosine over sine, or x over y. Those are all three correct. The one I guess I should have asked that more directly, but the one I was going for is cosine over sine. Let me ask you this. In order for cotangent to equal 0, it doesn't matter what this is. In order for cotangent to equal 0, knowing that cotangent is cosine over sine, what has to be 0 if cotangent equals 0? Cosine has to be 0. Okay? Think around the unit circle. Where is cosine equal to 0 around the unit circle? 90 and 270. Cosine is equal to 0 at 90 and 270. And I didn't write the full definition actually here, but the full definition of this right here is that 2 alpha has to be between 0 and 180. So between 0 and 180, where is cosine equal to 0? 90 degrees. So you could just assume that because cotangent equals 0, that 2 alpha equals 90 degrees. And then what would alpha equal? 45. So I think there was either a homework question or something on the review where that came up. And that, I suppose, it's possible for that to happen. Okay. We were good on number 5, right? We skipped that one? The ceiling of the room has a cross section that is an ellipse. So first thing I would do is, there's your ceiling. It's the top half of an ellipse. And it says that the room is 100 feet long. So starting from the middle all the way across is 100 feet, but I don't want the full width. I just want half of it. It's 50. You with me so far? And then it says the foci are located 32 feet from the right and to the left of the center. So I've already located the center. I can go 32 feet, and that's where one focus is right there. And what it's asking for is the height of the ceiling. But think about this. The way that I've drawn this ellipse, it's horizontal. So the equation of a horizontal ellipse is x squared over a squared plus y squared over b squared equals 1. That's the equation of an ellipse that's horizontal. What information do we have already just based off this diagram? What information do we have? We have a squared. What do you mean?
Well, it's 50 from the center or from the plane, so that gives 50 times 50.
No, you're right. Remember the endpoints of your major axis? That's your value of a. So if one endpoint is 50 units away from the center, then a equals 50. That's going to help us find a squared. Now, what does b give us on an ellipse? Don't think about this diagram here, but just in general, a squared is the endpoints of your major axis. So then b squared would be the endpoints of your minor axis. And that's what they're asking here. That's the minor axis, is the height. Well, there it goes. Come back. So our task now is just to find the value of b. That's going to give us the height. But we haven't used this. What does 32 have anything to do with anything?
B squared minus B squared.
That's your focus, yeah. That's that focus formula, c squared equals. So c equals 32 and a equals 50. So we have c squared equals a squared minus b squared. If we have two variables, we can solve for the missing one. So we have our two variables, a and b, or sorry, a and c. We can use that to solve for b. So c squared, that would be 32 squared equals 50 squared minus b squared. And from there, it's a pretty easy equation, I would say, to solve. So essentially b squared is 50 squared minus 32 squared. So what is that? We got 50 squared minus 32 squared is 1,476. You square root that, you get 38.42 feet. Was as bad as you thought it was going to be. Story problems usually aren't as bad as you think. You make them out to be worse than they are. Okay, I don't know if we'll have time to do all of the rest of the 5. So we have 6, 7, 8, 9, 10. We've got 5 minutes. Which one, if we had to choose one or two of them, which one do you want to see right now? Okay, we just need to plot a couple of points here on the polar axis, or in the polar plane. Point A, 3 for the radius, so we need to be on the third circle here. And then it needs to be an angle of 2 pi thirds. Now that's in radians. So you can either keep it in radians or convert it to degrees, knowing that this is 30, 45, 60, 90, 120, 135, 150, so 2 pi thirds. If we wanted to multiply that to convert it into degrees, pi cancel, 3 goes into 180, 60 times 2 is 120. So that would be on the third circle out at 120 degrees. So that'd be point A. Point B is on the second circle out, negative 45 degrees. And then point C is 60 degrees with negative 2. So the way we talked about this in class is if we went to 60 degrees at the second circle here, and then rotated that 180 degrees to there, that's how we deal with plotting points when they have a negative r value like that. So converting from rectangular to polar coordinates, what we have here are x and y coordinate pairs that need to be converted into an r and a theta value. So first we need this formula, r equals x squared plus y squared. So we have negative 1 squared plus root 3 squared. That's the square root of 4. So we have an r value of 2, and then to find theta we use the formula tangent theta is y over x. And then theta would be the inverse tangent of y over x. No, if we, sorry, inverse tangent, there we go. Inverse tangent. So if we use calculator to find the inverse tangent of square root of 3 over negative 1, or the inverse tangent of negative square root 3, that gives us negative 60. And the way we've always done this actually is just considering an absolute value. So if we did the inverse tangent of the square root of 3, positive square root of 3, this would come out to be 60 degrees. If we think about where this point is, though, negative 1 comma root 3, that would be in quadrant 2, which are angles between 90 and 180. So this is a reference angle. 60 degrees is a reference angle for an angle that would be in quadrant 2. So a 60-degree reference angle would be a reference angle for 120 degrees. So theta is 120 degrees. And it's the same deal now for part B. We still need to have an r value and a theta value. So square root of x squared plus y squared. Negative, or 3 root, square root of 3 over 2 squared is 3/4. And then negative 1/2 squared is 1/4. So 3/4 plus 1/4 is 4/4, or 1. Square root of 1 is 1. So r equals 1, and then theta is the inverse tangent of y over x. So 1/2 divided by square root of 3 over 2. If we have 1/2 multiplied by 2 over the square root of 3, then the 2's would cancel. So it's the inverse tangent of 1 over the square root of 3. And this is 30 degrees. But again, we need to consider where this would be. So this would be an angle in quadrant 4. So then 30 degrees is a reference angle. So I'm going to say that to make this into quadrant 4, we can call this negative 30. So theta actually equals negative 30 degrees. So for question 8, we just need to identify the coordinate location of that point on the polar plane. So it's on 1, 2, third circle, and the angle it makes is 7 pi over 6. So this is in polar coordinates. We need to convert this to rectangular coordinates. So we need x, which is r cosine theta, and we need y, which is r sine theta. So 3 times the cosine of 7 pi over 6, and 3 times the sine of 7 pi over 6. So 3 cosine 7 pi over 6. It's negative 2.6. And then 3 times the sine of 7 pi over 6 is negative 1.5. So then the coordinate pair would be negative 2.6, comma negative 1.5. So this is in polar coordinates, this is in rectangular coordinates. Right, question 9. We need to find the rectangular form of this equation. This is in polar form. So what I'm going to do is use this equation and also that equation. So what I need here is r squared, and then here I need another r so I can write r times sine theta. So I'm just going to multiply each side of the equation by r. So I'm going to multiply by r here, multiply by r here. So now I have r squared on the left, and then r sine theta. So that r sine theta gets replaced with that y, and the r squared turns into this x squared plus y squared. Okay, number 10. This is in rectangular form, so we need to convert this into polar form. So for this, I'm going to use the two equations x equals r cosine theta and y equals r sine theta. So this x is going to be replaced with r cosine theta. This y is going to be replaced with r sine theta. And then on this side of the equation, both the left and right side have an r in common, so I'm going to factor out that r right here, which leaves 2 cosine theta minus 3 sine theta. To isolate r, you divide by this expression over here. So we end up with 6 divided by 2 cosine theta minus 3 sine theta. All right. For number 11, graphing the equation of a conic when it's in polar form. This is from section 6.6. So first thing to notice is this is not 1. This should be 1. So your first step is to divide by whatever number is here, in this case 3. So I divide by 3 here, here, and here to rewrite the equation as 2 divided by 1 plus 2/3 cosine theta. And the reason this is so important is now this identifies E, the eccentricity, which will help us identify the conic. So since E is between 0 and 1, this is identified as an ellipse. Remember, if E is equal to 1, it's a parabola. If it's between 0 and 1, it's an ellipse. If it's greater than 1, it's a hyperbola. So in this case, we're dealing with an ellipse. Now, other things to note. Because cosine, that means we have a horizontal ellipse. And because it's plus, we're going to have the directrix to the right of the focus. So because we know it's a horizontal ellipse, the two vertices here and here are going to be on this line theta equals 0 and theta equals pi. So those are the two values I chose first. Let theta equal 0 and theta equals pi. These are going to help me find the vertices, which is part B. Location and polar form are the vertices. If this had been sine theta, then it would have been a vertical ellipse, and the vertices would have been on the line theta equals pi halves and theta equals 3 pi halves. But because we have cosine, I know it's a horizontal ellipse. So to first find the vertices, I'm choosing to let theta equal 0 and pi. So if I plug in a 0 here, cosine of 0, if this were the unit circle and this is 0 degrees, then the coordinate location of a point here would be 1, 0. Cosine of 0 then becomes 1. 1 times 2/3 is 2/3. 1 plus 2/3 is 5/3. 2 divided by 5/3 is 6/5. So the location of that vertex is the r value, 6 over 5, and the theta value is 0. So remember, this is not a coordinate location on a rectangular plane or the Cartesian plane. This is in polar form, where this is r and this is theta. So r equal to 6/5 is just barely beyond the first circle right here. And then 0 degrees means it lies on this line theta equals 0. So here's the point in polar form, 6/5 comma 0. Now, when we let theta equal pi, cosine of pi would be over here on the unit circle. The coordinate location over here is -1 comma 0. So the cosine of pi is -1. -1 times 2/3 is -2/3. 1 minus 2/3 is 1/3. 2 divided by 1/3 is 6. So the coordinate location of polar form at that point is 6 for r and pi for theta, which puts the point out here. If there were 6 circles, then this would be on the 6th circle, and then on the line theta equals pi. So those are the two vertices. Okay. Now, knowing that it's going to open to the left like this, or be more centered on the left, is because the pole right here was the location of this focus. The directrix is over here because we had that plus sign. So I knew that the ellipse was going to open this way around these two vertices, which means eventually it's going to cross the line theta equals pi halves and theta equals 3 pi halves. So that'll give us these 2 points here. So I plugged in first r equals pi halves right here. Cosine of pi halves would be up here at the unit circle. The location of a point at the top of the unit circle is 0, 1. So the cosine of pi halves is 0. 0 plus 1 is 1. 2 divided by 1 is 2. So when, that's actually a typo. That should be let theta, not r, I apologize. Let theta equal pi halves. So when theta was equal to pi halves, we got r is equal to 2. So 2 comma pi halves is the point right here on the second circle, and on the line theta equals pi halves. And then because of symmetry, we have a point that's reflected down here, but you could also just plug in 3 pi halves. If you were to plug in cosine of 3 pi halves, we still get 0 for that. 0 plus 1 is 1, 2 divided by 1 is 2, so we also have a point 2 comma 3 pi halves. And then for part C, graph the ellipse through those points, the two vertices here, and we had 2 other points to help get us a better shape of the graph. Question 12, this is from 6.7, parametric equations. We have parametric equations given here for t being any real number. So what I set up is a table. So t being the parameter means I can choose any value for t that's in this interval. Well, since t can be any real number, I just chose, at random from -3 to +3. So I can choose my values for t. X is going to be equal to 2 times whatever I choose for t. So if I choose -3 for t, then 2 times -3 is -6, and so on and so on. You can see I've just multiplied all of these by 2. This gives me my x values. Now my y values are also dependent on what I've chosen for t. So if t is -3, for example, -3 squared is 9, 9 times 2 is 18, 18 minus -3 is 21, 21 plus 1 is 22. So I've done that for all of these points. So these give me x and y coordinate pairs just right here that I can plot and graph. And just looking at a bunch of points in a table, it's kind of hard to tell what kind of graph this is. So I plotted a few of them. 0, 1. This one here was 2, 2. We had 4, 7 right here. Over on this side, we had -2, 4. And it appeared that they were graphing a parabola, so I tried to connect them the best I could. But it does graph a parabola. The vertex is right down here. It actually turns out to be right where x equals 1/2. And if even though the question did not ask for this, if we were to convert this to eliminate the parameter t, like some of your homework problems,
then what we would end up with is the equation of a parabola, y equals 1/2 x squared plus 1/2 x plus 1, I believe, or maybe it's plus 2. But anyway, it comes out to be the equation of a parabola for this, but you can see the graph right down here.